Anna Fuchs completed her master's degree and started a doctoral research at the University of Hamburg in 2016. Her research primarily focuses on parallel I/O compression techniques within distributed parallel file systems. Additionally, she is actively engaged in teaching in HPC-specific fields and have been involved in collaborations with DKRZ. Her research also extends to encompass system benchmarks, I/O aware scheduling, and I/O access patterns. Carsten Beyer is related to HPC since 2001 with building PC clusters for small distributors. In 2005, he started at NEC Germany as on-site support engineer for DKRZ till 2008, moving into DKRZ directly in 2009. His main focus are parallel file systems and resource scheduler.
Yeah, so good morning. What? So where we are and who we are. So we are a non-profit limited company since 1987. So our shareholders are the research societies, the large ones in Germany, so like the Max Planck Gesellschaft and Helmholtz Center, represented here by Alfred Wegener Institute in Herion, and the city of Hamburg, represented by the university. From my last talk here in 2017, our staff grew from 70 to nearly more than 100 people now. And we have, especially from our director, a small university group for I/O also included in our facility. So our current system is called Levante. So it's a Bull Sequana with about 3,000 nodes, 370,000 cores, AMD Milan. So from the first top 500 benchmarks, it was 14 petaflops, not included our GPU partition, which is currently 60 GPU nodes, each equipped with for NVIDIA A100 with 80 gigabyte memory. So it's a hot liquid cooling system, so it's pretty nice. We have attached 3 file systems. So we have home, which is about 120 terabyte based on NVMe. So home directories and our software tree. We have enabled user quota, and we use also PFL and striping directories over metadata servers, but only for the top level directories, not to stress the MDTs too much. Then we have our large file system called Project. So it's nearly 120 petabyte hard drive based storage, which contains our more than 300 projects from our customers and scratch directories for each user. So we have about 2,500 users. And for each project and each user, we have Lustre project quota enabled. We use also here PFL and striping the directories over MDTs. Then we have something what we call fast data. It's more a test system or test storage containing 200 terabyte NVMe and 3 petabyte hard drives. So there we have a collaboration with DDN and Atos for testing new concepts, workflows like hot and cold pooling and data migration. We have also a pretty large tape archive with about 80,000 slots and 10,000 slots remote in Garching, also near Munich. So currently we have about 158 petabytes of climate data. So the increase last year was 25 petabytes, which is less than expected. In total, we have more than 700 petabytes of capacity. So in the beginning, we had a lot of problems with our IB fabric that caused IB flaps on the compute nodes, most times Lustre hiccups. disconnection for the Slurm job, so the Lustre hiccups were sometimes on the home file system, sometimes on the larger systems. That caused problems in many ways. So the actions we had to do, the restriction of CPU frequency and disabling turbo mode. We had to install from NVIDIA Mellanox new firmware that on the switches that was especially developed for us and another customer. And we had to put a lot of ferrite cores on the InfiniBand cables. What we also found out that some single jobs with toxic Lustre I/O affect the whole InfiniBand fabric. That was causing large runtime deviations for other larger MPI jobs, and there we started to isolate or separate then these nodes into a single rack and single switches. But the best thing that we made then this year, we separated the Lustre traffic in the IB fabric with virtual lanes. And since that is pretty fine, and Anna will give more details on that later. With the collaboration with the hot and cold pooling, so with this file system with the NVMe and as hot pool and the 3 petabyte as cold pool. So we had a hackathon from the Max Planck Society, and we had to copy a lot of data there. So they started to use it with the often accessed data on the hot pool, not accessed data on the cold pool, and automated two-way migration between both pools. But it lacks some things. So currently we have no monitoring in place which files or which data was migrated and in which direction. So it was said that we got this in a future release of the exascaler. In the meantime, we do some own reports by using LIBE or the LIPE scan. So we scan the MDTs that we do every 6 hours, and then Max Planck has some scripts to analyze the data, which files were accessed in the last time, in the last hours. So we use it also for some other things. So on our previous system called Mistral, we had Robin Hood. We stopped that after a Lustre update. At that time I was, I think, 2.11. And after that, my Robin Hood was no longer working. And now with the new system, we started more with this LIBE. And so we scan the metadata servers once per day. So and after that, we do some analysis with a Python script of the JSON output. So the runtime for the scan is currently, depending on the usage of the metadata servers, up to 8 hours. But I could fasten that by using more CPUs. Currently, I don't use all CPUs. So the runtime afterwards is 4 hours for a single CPU job on Slurm for about 1.6 billion JSON lines collected from 8 MDTs. So and we use this for generating reports for each project, which user uses how much data in the project as overview for the principles of the project. And the good thing is we don't need extra hardware as needed for Robin Hood. So all is done directly on the MDS, MDT. I used the same thing and found out that 36% of our data is not accessed for more than 1 year. So currently we are using about 70 petabyte of our 120 petabyte file system. So it's a lot of old data lying around. So it's much too expensive. Other thing is, currently I would like to know if there's also much data duplicated or in many ways there. So I would appreciate if somebody has experience or knows some tools, what the best way to find out. I'm not sure if deduplication would be a possible way in Lustre. That is something else. One of our challenges was to connect both systems, because we had to copy data from Mistral to Levante, and we have also some external nodes not on the IB fabric. And we found out that LNet router would be a bottleneck for transferring the data. So Atos and DDN created on Levante, here on this side, additionally to the 10.x IP addresses, a second network with public IP addresses, and we created then additional TCP L network. And on the other side, but only on a few compute nodes, we made the same. So we could mount on this side this Lustre, and I was able to copy about 45 petabyte of data in a few weeks from one side to the other, because then this system was dismissed last year in summer. So, as I already said, the purpose was to copy that, and we have a lot of VMs outside the IB fabric that uses the data and is exposed to the internet, because we are delivering the data also on the climate community worldwide. So we use currently node maps. This is also for the servers and VMs that are outside of our IB fabric. What Andreas already said yesterday, we have this already in our exascaler version, so that we could, like on NFS, so like the exports file, separate the VMs in read-only and read-write, and it is forced directly from the Lustre servers. We could also map users and groups to special defaults. And we have a small script running where we have some kind of map file, and then it will give us the LCTL commands to add or remove hosts from this list. And that's pretty good for us, and so we could separate that to read only and read write. We have quotas that give us sometimes a headache, because we have different projects from our different shareholders, and sometimes members are in different projects, and sometimes they want to move data from one project to another, which is currently not really possible with project quota enabled, because each project has its unique project ID. So MV command looks like a long-running CP. So for these movements, we tweak recursively the quota ID on the source directories. So put the with LFS project the project ID from the target there, and after that it could be moved again, just like a metadata operation, and it's pretty fast. For this next GEMS hackathon, I was using MPI file utils to copy the data from our large storage to the fast data one. And the other challenge was that the directories for one simulation was from 1.7 terabyte up to 480 terabyte, but that ranged from 200,000 to 940,000 subdirectories per simulation, and from about 160,000 to 35 million files per simulation, and all between just 5 and 15 megabytes in size. And there were 33 simulation runs to copy. There was how to find the best number of nodes for copying. That was then about 3 to 4 nodes with about 24 to 36 MPI tasks per node. I used some kind of chunking that because MPI file utils creates all directories, all files in the beginning. So, and then with some chunking of 100,000 or 500,000, just create sets in batches. And that was better if a job was failing to restart the job, because if I don't do it, or if you don't do it and it fails, it will delete everything and you have to start again from 0. So, and now, Anna, that's your part about virtual lanes and network.
Thank you, Carsten. So let's talk a bit more about network problems. And just for the beginning, the DKRZ network infrastructure is a massive fat tree with 3 levels of switches you can see in the picture. And in the bottom, you have a lot of compute nodes which are bundled. So there is a bundle of compute nodes connected by every L1 switch. And another grouping process is on the second level. You have the neighbored 4 L2 switches which bundle again a lot of more compute nodes, and they call this virtual group SL, just for the naming. The storage not presented in this picture is almost always connected only to level 1 switches. Just another picture for better understanding. These would be the ways the communication can take if 2 compute nodes are communicating from different cells. This is another representation of the infrastructure where you can see the compute nodes on the top and the bottom and all the switches in the middle. And in the right corner you can see the storage servers, and maybe you can see the tiny gray lines that show the connections from every storage server to some of the L1 switches. So in the case the client request, I/O request, does not match this connection to the server, then the I/O request will make a few hops over the second and third levels of switches. So far about the network infrastructure. Now coming to the actual problem, which is network congestion. And like Carsten told you, running a big MPI job parallel with a big I/O job can cause problems. And we've set up a test for that to benchmark it. We've used the NumIO benchmark, which we've initially designed to make measurements for compression feature inside of Lustre. But in this case, it's just running a lot of computation and hello lines exchange over 35,000 of iterations, and every job run on just 2 nodes. One node was coming from cell 2 and the other node was running on cell 9. And we've made additional runs where we have a collective mode, where we just put a lot of all-gather collective operations every 70 iterations on top of the baseline. And the other mode was putting a bit of I/O, I think every 200 iterations on top of the baseline. And you can see it on the left side of the diagram. The non-toxic case was just a measurement on a more or less empty network for these cases. And then we've put another background job. So at the same time, we've run a big toxic I/O job where we read a file per process in parallel and just compute the checksum with MD5 sum per file. And this was running on one node, but in the same cell 9 as the other node from the other job. And you can see in the middle and on the right side the diagrams which show the impact of this background job. There are two variants of that, A and B, which are actually varying in the number and sizes of files and the stripe count. But in both cases, you can see that the collective communication suffered a lot due to the network congestion. This yellow bar on the right side, we can see even that the time was doubling. Although it looks like the pink bar is also a bit suffering, so the I/O was a bit slower, it's actually not the case because this delay is due to the portion of the hello lines exchange, which is again a bit of MPI communication, and this is a fixed part of every test. So the pure I/O was not really slower, was not impacted by the network congestion. And if you take a look at the vampire traces, you can see this picture, and you can, I don't know where the beamer shows it correctly, but maybe you can see the idle waves in the bottom. So we can conclude that when the MPI requests traverse this heavily congested network, they can experience maybe just a small delays, maybe in a range of a few microseconds, but aggregated, it results in huge idle waves, you can see especially in the middle, and this slows down the application a lot. And as Carsten said, there is a solution for that. They introduced the virtual lanes on the same InfiniBand hardware. So the basic idea is to separate the latency-sensitive traffic from the large I/O traffic. But this was not made based on the qualification of the request. So they don't really ask every request whether you are latency sensitive or not. They just made a basic assumption that latency is critical between compute nodes, sending almost always MPI messages around, and it's not really critical within the file system. So this solution helped a lot and solved actually the problem tested there. You can see on the right side, the measure times are almost identical with a non-toxic case. But anyway, I was a bit questioning, especially the second part of this assumption that latency is not critical within a file system, and I've constructed another test setup where we have a small, sparse, not even necessarily random I/O traffic that can be latency sensitive, and therefore we have a reading benchmark that reads every 4 bytes, the first 4 bytes of every 1 megabyte block in a 16 gigabyte file, so very big gaps in the file. And this is actually representing a lot of post-processing, visualization, analysis jobs on the massive simulation data, and also representing the machine learning applications. And in green you can see this baseline run where the data was cached on the server, so there is no disk I/O. The blue one is with disk I/O, and it's took significantly longer because this is also a really bad pattern for spinning disks. And these both measurements were made on more or less empty network. And the black one is the impact of, again, this background toxic I/O job. Again, server cached, and we have an impact factor of about 5 or 6 that slowed down this small run. So you may say that I'm killing I/O with I/O. Well, yes, maybe, but still I believe that the things don't need to be this way, at least not always. And I thought about a few of the solutions, and one of them, at least an opinion, would be just to say it's not a problem at all. At least it's not our problem, because such an access pattern is not an HPC use case. I actually don't agree with that because, as I've said, it's a representing use case for post-processing stuff, and I think it is an HPC use case because they need the HPC resources to run the jobs. And the suggestion to solve this would always be to duplicate all the data and move it to additional storage system, which is more suitable for such for this type of access pattern. I think Carsten wouldn't agree to duplicate 130 petabytes of data and maybe 700 of the archive, so I don't see that this would be a solution. Another opinion would be just to fix the applications because it's really a horrible access pattern. But again, I don't see to how extent you can really fix it. Maybe for the post-processing, making some optimizations, but it's out of our control, and it's actually out of the control of the HPC users because they rely on a pretty deep Python stack, and their middleware modules are interacting in some magic way. Nobody has the actual control about that, and I'm not sure how much you can really optimize the machine learning applications. So don't be scary about the chosen block size of 4 byte. You could take also 4K byte because of the internal buffer sizes and page sizes. There is anyway a bigger block that is sent over network. So I think it's just a valid access pattern. Another solution would be to use the Lustre network request scheduler policy called token bucket filter. But as far as I know, it's just able to restrict the amount of requests statically per job or maybe use our project, and I don't really see how it can dynamically help if you have this situation of concurrently running jobs killing each other. So it's not taking the quality of the request into account, as far as I know. So maybe it would be a good approach to implement kind of a virtual lanes inside of Lustre that would maybe make a better housekeeping of the requests and put some priorities on them. And I wouldn't rule out that I just missed the solution, which is maybe already there. So if the topic is of your interest, maybe it's worth a short discussion. And so far, I'm done with the content. Thank you for listening.
So, do we have any questions?
So you say that you didn't want to use any Lustre gateways, but if you can put back the schema of your fat tree, please, on the screen. Can you go back to the huge fat tree graph? No, come forward. Not the fat tree. The one with the fat tree, sorry. If you don't have it. Yeah, this one. So it looks like you have like plenty of nodes under the L1 and L2, and the issue when you try to access Lustre is that some nodes has to go back up to the L3 and go down somewhere to access an OSS. So what about like having under, let's say, the L2 area some LNet routers and set up the route to ensure that all your nodes are not going up to the L3 but use the LNet gateways to access the file system?
So this was the design of Atos.
Yeah, I know. And I'm not responsible of it, but still I'm working from Atos, and the funny parts for the whole story so I work a lot with Météo France. They don't have a fat tree, they have a Dragonfly Plus topology, and they complain about the complexity of the DF Plus, but it looks like you're exactly facing the same kind of issue with a fat tree. So at the end, we can think about that. And also they don't have like the LNet gateway, so they had the same kind of issue where they have to go back to the level 2 of the DF Plus and then go back somewhere else to access the OSS. And I was like, maybe a better solution would be to have like gateways and ensure you don't use the top of your topology when you are doing clusters.
So we got a proposal from Atos also for some recabling and other setup of the network, but they were not sure if it would help. So in this case, we were talking also with other data centers and also I think with ECMWFF. And so they had this solution with the virtual lanes. So they got it first, and then we got the same solution at DKRZ. And that works for us.
Also, we did implement like the virtual lane from the beginning to avoid those kind of issues. But
we got this virtual lanes this summer.
Yeah. So, but we need to speak about how you did configure virtual lanes, and it looks like we are facing the same kind of issues. So we have to exchange, I think. Thank you.
Other questions?
I have one. Just about the LIP, the scan metadata you have run tool. What is the impact on performance? Because you have said that you don't need Webinode server. Of course, you need specific hardware. But if you run, for example, MD test when you are running the scan, have you an evaluation of the impact on performance?
So we don't. I just use the scan, and I don't use anything else from that.
Okay.
Okay. So thank you.